Our next set of definitions that we're going to look at have to do with the extreme values of our function. And this is going to be one of the one main ideas we're going to be looking at in a lot of our lessons for this. We're going to be interested in optimization, finding where our function has the largest value or the smallest value. And so that's what these definitions have to deal with. So we call these the relative maximum and the relative minimum, or we might call them the local maximum and the local minimum. And they have to do with sort of a high point or a low point on our graph. So the local maximums, those are the high points. So in this little example here, this first graph shows what a local maximum might look like. So this is a local maximum at x equals c. But what's really going on? So a local maximum value of function f is a number f of c such that f of c is greater than or equal to f of x. So our function value at this maximum is greater than or equal to all of the other function values near x equals c. So what that means is if we have our high point, if we look at a little interval surrounding that high point, it's the highest one there. So this is kind of like think of maximums as like a mountain peak. There might be other mountain peaks out there, but in the immediate area, it's the highest point on our graph. So think of maximums as sort of like a mountain peak on our graph. Now what about a local minimum? Well, a local minimum, that's what we're seeing over here in the second graph. So this one shows a local minimum at x equals c. And let's read through the definition. So a local minimum value of function f is a number f of c such that f of c is less than or equal to f of x for all x near c. So what that means is a local minimum is a low point on our graph. There might be other points further away that are lower, but right around x equals c, if we can find a little section of our graph there where that is the lowest spot on our graph. There might be other low points out there, further away, but right around x equals c, we can find this little section of our graph where that is the lowest point. And what's happening, if we look at these graphs, what's happening is there's a switch, there's a change happening right at x equals c in each of these cases. So for the local maximum, what's happening is on the left side, our graph is increasing. So over here, our graph is moving up. And then at x equals c, what happens? Well, it switches, and then it starts decreasing on the other side. So here we switch from increasing to decreasing. Now for a local minimum, what's going on over here? Well, on the left side, we're decreasing, so our graph is falling. It's getting lower on this left side. And then we hit our local minimum, and then the graph starts increasing on the other side. So these places where our graph switches from decreasing to increasing are going to be important. And this is where we're going to have local maximums and local minimums, potentially. All right. So, and this definition, we just want to be careful of it. Be careful with it. So we're defining the local max value. So we just want to point out the actual function value, f of c, is the local min max value. So kind of the key word here is value. So we're looking for, when we talk about the local max value, we're talking about the value of our function. And x equals c is still important, But that's sort of like the location. Where does the maximum actually occur? It occurs at x equals c. So f of c is the actual value of our function that's large or small. And then where that actually occurs is at x equals c. So we think of the x value as sort of like the location, and then we think of our function value as sort of like the height. All right, so this is for local maximums and local minimums. So these are like mountain peaks or low points, but there might be other mountain peaks out there, or there might be other low points out there. And so we're also going to be interested in not just the high points, but the absolute highest point or the absolute lowest point. So sort of like the Mount Everest of mountain peaks on our graph. And we call these the global maximums and global minimums, or absolute max and absolute min. So these are essentially the highest point on our graph or the lowest point on our graph. And so the definition here is going to be very similar. It's just kind of one key difference. So for instance, the absolute maximum value of our function f is, again, it's the number f of c, such that f of c is greater than or equal to f of x, where x is now can be any number in the domain of f. So the difference here is between absolute maximum and local maximum. Local max just had to deal with x near c. So we just found this little interval surrounding x equals c, and yeah, it was the high point there. But now with absolute maximum, what we're doing is we're extending through the entire domain of our function. And so the absolute maximum is the absolute largest value that our function ever takes on. Or for absolute minimum, it's the value of f, the absolute minimum value of f is a number f of c, such that f of c is the smallest value. So it's less than or equal to f of x for all x in the domain of f. So again, the difference here is we're talking about all x in our domain for our absolute min, whereas for local min, it's just in a small little section of our graph. So here f of c is the smallest our graph gets in this little section. Absolute min, it would be if we extended through our entire graph. All right, so let's look at just two examples here. So in this first example, let's see what we have. So we have this section of graph that extends between two endpoints. And what we're seeing at this point here, -1, 5, we're seeing a relative max or local max. And over here, we're seeing a local min. So what is the local max is this high point here. The local min is right here. Now these happen to also be the absolute max and the absolute min for this function as well. So the absolute max is 5. So the y value there, that's our actual function value. And the absolute min is 1. So our function value there. And the absolute, I probably should have left a little space here. So the absolute max value is 5, and that occurs at x equals -1. And the absolute min value is 1, and that occurs at x equals 3. That point right here. Now what about on this second graph? What would be the absolute max and the absolute min? Or do they even exist? And let's take a look. So if we're looking, and the way we generally read graphs is when we get to an end like this and the graph just kind of trails off, we interpret it as it just keeps going in that direction. So notice over here, we kind of had these endpoints that specifically said the graph ends right here and the graph ends over here. Over here just kind of trailed off. So the way we read that is we think of it as the graph just keeps going in that direction. So this graph still has a local max right here. So there's a high point right here. There's still a low point over here. But now the absolute max and the absolute min has changed because we've kind of extended this right side further up. And so the absolute max here is where do we want to put this? Put it over here. Yeah, because I want to actually write something. Well, we'll put it right here. Absolute max is equal to 6, and that occurs at x equals 5. So this is our the absolute highest point on our graph. We can't get any higher than this. So yeah, this other point is a local max, but this point over here is a bit higher, and it's the highest our graph ever gets. Now for an absolute min, this graph doesn't actually have one. So we have a low point right here, but eventually if we read far enough to the left, we eventually get that low, and then we keep getting lower and lower. And there's no end to how small our function actually gets. So the absolute min is there is none. So, you might think, if I thought this point, say, was my absolute min, well, eventually I could find the graph goes below that, and I could find another point that's lower. So I might think this is my low point. But eventually the graph keeps going, and it gets lower than that. And so I could keep playing this game of getting lower and lower on that section. And so the fact that I can get as low as I need to means there's no absolute min. So there's a local min, but there's no absolute min. So having this absolute highest point or the absolute lowest point is sort of a special property that not every function has. And as we'll see, it sort of depends on the interval. It depends on the function, but it also depends on the interval we're looking at. So we'll see that in another lesson. So it's worth noting here, as these graphs show, a function may not have an absolute max or absolute min. So these are special. And for an absolute max or an absolute min, they can occur at a local max or a local min, as we saw in this first graph, or they can occur at an endpoint. So keep this in mind for the next lesson. So we're going to see how to actually find the absolute max and absolute min values for a function using calculus in the next lesson. But keep this in mind. They can occur, as we saw in the first graph, they can occur at the local maxes or mins, or as we see in the second graph here, they can occur at an endpoint. All right, so that's the definition of maximums and minimums: local max, local min, absolute max, absolute min. So we're going to be working with these definitions over the next bunch of lessons. So feel free to come back here and just freshen up on these definitions. All right, so a few more definitions. The next major category we're going to be looking at has to do with the shape of our graph, concavity. So we'll see you there.